is, okay, let's make these devices in such a way they can also communicate. The applications that then we can create are many. Like, for example, okay, this would be like, for example, this office. We may embed one of these really small, by small I will show you later which numbers I'm talking about, really small components into almost everything, but not only on things. You can also try to integrate those things on or in us. Why? These nano things that we are targeting are comparable in size actually to the human cells, which means that the nanoscale actually is by default the same domain, the same sizes that many of the biological components. We are talking about that one of these nano things, I will tell you later, they are around, let's say, 100 micrometers in diameter. Molecules are in the order of a few nanometers, bacteria are a few hundreds of nanometers, so we are in that domain now. So of course, many of the applications of this will be in the biomedical field, but that's not the only case. So what's the Internet of Nano-Things? Okay, it's adding a new layer to what would be the Internet of Things, which is, but not a layer in terms of larger things, but of resolution, of small, of being able to go to the nanoscale and detect new things. Again, this is within the introduction, let's say the following. We are talking about communication, and we need these devices to communicate. When Dr. Ekil, 5 years ago, started working on nano-communications, they say, look, it's really difficult to make these devices communicate in the classical way we think, acoustic wave, or electromagnetic, or optic. And actually, the first option for our lab was to look at how cells communicate. Cells communicate, bacteria communicate, but what they do is they exchange molecules. This is a very interesting option, and actually this is one of the divisions in the lab we have of people working on molecular communication. But short after he started working on that, we got some interesting feedback actually after some of the first papers saying, well, you cannot ignore the applications of some of these nanomaterials for optical and electromagnetic communication. So this is where my PhD starts, which is to talk about electromagnetic communications at the nanoscale. The application, nanosensor networks, the Internet of Nano-Things, any that you can come up with. So okay, with this big picture in mind, let's go step by step. Let's go first and look at how this nano device can look like, how it's going to be made of, and which will be its capabilities. Okay, if you ask us, okay, create a conceptual image of a nano thing. Okay, you can see this picture. Some of you may say, but this is a nano brush. No, it's not a nano brush. It's a nano thing, and each component here has some meaning. I will explain them one by one, but for example, the power unit is made by these nano wires that harvest energy. We'll have some processors, some memory, some antenna, some sensors. But let's go one by one. First of all, I mentioned these nano things will have extremely high sensing capabilities. If today, right now, we go to Google and look for nanosensors, we will find thousands of papers on nanosensors. But what they call nanosensors is what, for us, coming from classical sensor networks, we'll think of the sensing unit. These nanosensors are usually a few hundred nanometers in size, and they are able to detect different types of magnitudes at the nanoscale. Usually, they are based on a kind of transistor-like behavior, which is, we can place, for example, one of these nanotubes or nanoribbons between two electrodes, and then we can measure the current that is able to flow through here. When this tube is bent, there is a change in the number of electrons flowing. We're talking about few electrons, we're talking about nanoscale. So this change is saying, look, there is a deformation, which means that there is a physical force applying there. Similarly, when there are different types of molecules which may collide or get attached to the tube or to the ribbon, when there is a charge exchange between the molecules and the tube, this again will affect the propagation of the movement of electrons, which will turn into some changes in the intensity, the electrical current at the end of the electrodes, so which means, okay, we are sensing something. More interestingly, if we take one of these nanotubes or these ribbons and we hybridize it by attaching some, for example, antibodies, then when these antibodies will detect the presence of different antigens. Antigens are the molecules that identify different types of infectious diseases. So when these antibodies will attach to the antigens, again, this creates a chemical reaction. This changes the charge on the tube, and this affects the current as it's flowing. So that will be the principle of these nanosensors. And there have been nanosensors for all types of things, from glucose levels or cholesterol to cancer cells or even early detection of Alzheimer. Okay, we have the sensor, but we will, right now, let me say the following. Those sensors, they exist, they have been manufactured, but usually they are placed in the right place, and now in order to read their measurement, you have to take them out, and you have to use external big tools to see what's happening, to actually read their measurement. So what we want to do is to make them autonomous and to communicate. And to do that is why we create this nano thing, not just a nano sensor. So of course, we will need some power. Again, if we look for what they call nano batteries, for example, we will see that nanomaterials can be used to improve the quality of existing batteries. They can have like higher capacity or faster charging rates. That's very interesting, but who is going to go and recharge or refill one by one those batteries? Having batteries is fine, but we also need harvesting systems. There are actually some few groups working on self-powered nano-devices. One of them is at Georgia Tech, Professor Zhongling Wang, and what he's doing is he's getting these arrays of zinc oxide nanowires, and these wires have this piezoelectricity effect, which means that when you bend them, you create actually some tiny current. If this current actually, you can end up charging an ultracapacitor, in this case ultra nanocapacitor, and you end up obtaining some energy. This is not science fiction. You can go online, you can go to his website. There are some animations and some real videos on the amount of charge he can gather at the end, how much energy he can harvest. The idea is to harvest energy from, let's say, the vibrations in this room or the bloodstream, many things. So that's, again, something that is existing. We have some work on this because one of the first questions that people say, okay, energy problems. Yeah, there are energy problems, but they will be solved. What else? The processing unit. We don't need a supercomputer in each nano thing, but we may need some, even if simple computations. So, well, actually, all the processors, the building block right now, it's like an FET transistor. What do we do with this transistor? Well, right now, many of the new laptops are based on 32 nanometer technology. 20 nanometer technology is around the corner. But for example, the smallest transistor that has been built by today, it's just 1 by 10 carbon atoms, which means less than 1 nanometer in each direction. This was in University of Manchester in UK. And again, they were showing that, first of all, with graphene, carbon, you can make smaller transistors, but in addition, due to some fancy electron transport properties, you can also make these transistors switch really fast. So we are talking about smaller transistors switching at very high frequencies, called starting point terahertz, teraflops. Memories. Well, again, we may need some memory, but how do we do this? Well, for example, this is nothing new. Back in 1959, Richard Feynman, who is like considered the father of nanotechnology, in his talk, which was entitled, "There is plenty of room at the bottom," but by the bottom he doesn't mean the bottom, he means like the basis of every molecule. He was saying, look, if we create a system in which a single atom is contained within, is able to store a single bit, then we're talking about single atom memories. However, you can understand that atoms in close vicinity can interact. So what he did was to say to define some kind of unit cell able to contain 1 bit. And this unit cell was 5 by 5 by 5 atoms. So 125 atoms to store 1 bit of information. This is actually huge advance. And in this case, we're comparing, for example, to the capacity of storing information of DNA, which is supposed to be huge because it's kind of chemical storing. I mean, DNA uses 32 atoms per bit. With this, back in 1959, we were talking about 1 bit every 125 atoms. This was an idea. What do we have today? Well, today people are working on atomic memories like magnetic memories or gold nanomemories. Again, this is still not ready. I'm not saying that today you can have a rewritable single atom memory. But people are working on that, and we may end up to something. But in any case, I'm not a processor guy or memory guy, or with Dr. Akilvis, our focus is to talk about communications. So which are the communication options when we go to these nano devices? Well, mainly in our transceiver, in our communication unit from a typical sensor, we have the transceiver, which does some signal processing, generates the necessary signals to drive the antenna, and the antenna. If we look at today what's the smallest transistor that can be used with radio frequency applications or components, we will actually, interestingly, end up again talking about graphene. Graphene, there are mainly group in UCLA, a group from IBM, and recently a group in MIT. They are all trying to obtain fastest transistors in graphene. Why graphene? As I told you before, the transport of electrons in graphenes is really special. Actually, it's really fast. Transistors can almost ballistically move for a few micrometers, which is a lot compared to other materials such as silicon. So what they are doing with graphene is they already shown transistors that even if very simple process, even if very, let's say, not optimized design, they are able to operate at hundreds of gigahertz. So actually, they say that they will be able, maybe 1-2 years at most, to obtain components for this nano-transceiver able to operate at terahertz frequencies. For example, one of Thomas Palacios in MIT right now, well, it's a MURI project. They obtained this, ARO is funding them in order to obtain, well, graphene components for terahertz nanoelectronics and communication. So that's exactly what we would like to. But how about the antenna? Well, we need to make an antenna very small. We know that if we take a classical dipole, for example, a metallic dipole, and we make it really small, what will happen is that, well, the resonant frequency will go up, up, and up. In addition, not only will have very high resonant frequencies, which will mean that we will have problems in terms of communication with very limited range, but in addition, due to the problems in making very small structures out of conventional metals such as copper, we will have very low efficiency radiating. So we thought with Dr. Achilles, how about doing also antennas based on this graphene? There were some papers out there talking about nanotube-based antennas. The main problem of nanotubes, even if they were very fancy at some point, because maybe they were discovered in 1991, so people could work with them for a long time. The main problem of nanotubes is that at the end they are cylindrical, they are round. It's not easy to work, manufacture, and integrate them. So can we do something better? We said, okay, let's start with graphene. The nice thing is that our starting point is that due to the several quantum effects that affect an electromagnetic wave trying to propagate on graphene, due to that, the resonant frequency of a graphene-based antenna is actually 2 orders of magnitude below what we would expect of a metallic antenna. The main reason for that is that the antenna does not resonate at the classical, let's say, resonant frequency, but at the so-called plasmon frequency. What we did in this paper, first published as a conference paper last year in the European Conference on Antenna Propagation, and now under revision for journal, is that we developed quantum mechanical framework starting from the type banding model, which allow us to obtain the transmission line properties of a graphene nanoribbon. From this ribbon, we were able to obtain different parameters, such as the contact resistance, which at the end will be related to the input impedance, the quantum capacitance, which is related to the fact that when you make an antenna or any structure that small, electrons cannot have a random energy value, but the energy values are quantized. This is the origin of quantum physics. So because of this extra energy that electrons need to have in order to reach the right energy level, we define this quantum capacitance. This is something well known for the material. Similarly, in order to create a wave, we need these electrons to move back and forth. So there is actually some extra energy that they need because they are moving not at their natural energy level, but above what they were supposed to have. So this is a kinetic inductance. So with all this framework, we were able to end up obtaining the transmission line properties of this antenna or nanoribbons, and then playing with antenna theory, we were able to show that for a 1 micrometer long antenna, a nanopatch antenna, if you want to think like that, we would be able to radiate approximately at the terahertz band. Okay, well, at this point is actually when everything starts. We said, okay, terahertz band, does it make sense? Well, it makes sense. It matches the results from other groups that were working before on nanotubes. It matches the results on some other people who is working right now on that. But at the end, many people say, well, if I don't see this, I don't believe it. And I understand them, even myself. My research is that sometimes you say, oh my God, maybe this is just a bunch of smoke, which is not. So actually, because of that, we are now partnering at Georgia Tech with 2 more universities, and we are trying to build these antennas and to actually measure them. I hope, I was telling to some of you this morning, I'm planning to graduate, let's say, in 1 year, 1 year and a half. I really would like to see some of this working before, and I hope that we will do it. This is fine. We actually, these partners we got, there is this professor at MIT working on graphene electronics, and another professor in UT Dallas, which is an expert on transceiver for terahertz. So again, we have some numbers. We see that the antennas are able to radiate at terahertz frequencies. People working on transceiver are able to do components, again, also based on graphene and working at terahertz frequencies. Okay, well, at this point it looks like everything is nice, but let's just stop for 1 second. I mentioned that there are nanosensors. They will be eventually nanoprocessors, nanomemories, transceivers. But actually the main problem right now is how to integrate all these components together. We are talking about extremely small things that even with the smallest tool that you can imagine, it's really difficult. One of the techniques that has been proposed to assemble these different components actually is so-called DNA scaffolding. This sounds like biology, but this work is being done by IBM. This is how they suggest that you may eventually end up connecting different components in your computing architectures. The idea is the following. If we take the typical complementary DNA sequence and we split it up, we can attach one of the sequences on top of the component that we want to attach, and the other sequence on top of, for example, a silicon substrate. Then, if we mix this and the components in the same fluid medium, at the end, we will have everything connected and moreover connected in the right place and in the right orientation. Again, we are still talking about some very, let's say, basic prototypes. But again, let's be realistic. Is this impossible? No, impossible is not the word. Is it challenging? Yes, it is challenging. I mean, I cannot tell you that we will have these nano things working in 2 years. No, that's impossible. That would be misleading. Okay, so now that we have a clear clue, more or less.
You look at it as 10 years.
Yeah, indeed. Actually, we first say 5, now we are moving to 10. But that's one of the main challenges. Okay, so now that we more or less know what can we expect from these nano things, what can actually create, let's talk about communication and networking challenges. First of all, we talk about antennas radiating at terahertz frequencies. Well, you can understand first reaction, oh my god, these are very high frequencies, you will not be able to do much. Well, let's think about that. First of all, there are groups already working on terahertz communication, but they are targeting transmission distances in the order of a few meters. It's not realistic to assume that from a nano thing, which may be few micrometers to transmit over meters, we might achieve millimeters, centimeters at most, but not more. The main reason that at their scale, what they are doing is actually to focus at 300 gigahertz window. The main problem in the Terahertz band is molecular absorption. Molecular absorption defines several windows when you try to go above 1 meter. So what they are doing right now is to look at 300 gigahertz. Why do they do that? Well, because again, they are going above 1 meter. But for that we're going below, is it really that bad, the molecular absorption? So what we did is, first of all, try to obtain a propagation model for terahertz band communications, in which we play with the number of molecules we may have, so we can actually place, I want a medium which is composed of this type of molecules or that type of molecules. And then we play also with the distance and all these type of things. And we obtain expressions for the path loss and the noise. And then we try to see how, by using some capacity analysis, we try to see, okay, what is better? Should we, like people do for macro scale, focus on a single transmission window, or should we spread the power over the entire window? So to come up with some solutions, what we did is actually to do a capacity analysis for different power allocation schemes. Okay, this is really fast because you already know part of this.
What is a power allocation scheme in this context?
Well, the way mainly it means, should we take our energy and just create a carrier, for example, at 300 gigahertz? That would be an option.
Carrier?
Yeah, carrier. Or instead of that, maybe we want to spread the power and transmit these very short pulses, which are kind of wide, over the entire band from 0 to 1 up to 10 terahertz. That's two of the options. The other way, well, if we're doing a theoretical analysis, what we can also try to do is to do some kind of optimal power allocation scheme, typical water filling. We have a huge band, we have some resonant frequencies, we try to do water filling. That's what we will end up showing. So for the path loss, again, path loss, we know this is composed of the spreading loss and the molecular absorption loss. The spreading loss depends on frequency and distance. And the nice thing is that the absorption loss depends, as I mentioned before, on the type of molecules we have, how many molecules we have, and well, how are they distributed in space. Which is the idea? Okay, what is the origin of molecular absorption? If we are explaining everything with electron or molecule level, let's try to understand molecular absorption also at the molecule level. When some molecules are irradiated by an electromagnetic wave, they internally start vibrating. Terahertz radiation is not ionizing. We cannot break the components of the molecule, but we will make it vibrate. This vibration, this conversion from electromagnetic energy into kinetic energy inside the molecule, it's the loss from the communication experience we expect. And again, my objective now is not to go through the math, but I invite you to go through papers, and one of them is going to be in transaction wireless communication by the end of the year, and the other was in ICC 2010. But the idea would be the following. Let's try to represent the path loss in this figure. Here in the x-axis, we have frequency, from 0.1 up to 10 terahertz. In the y-axis, we have distance, from 1 millimeter up to 1 kilometer, logarithmic scale. The color in this figure represents the path loss in dB. Just for representation purposes, we add anything above 120 dB is painted red. So we can clearly see some of the windows that otherwise we would not see. Okay, what do we start seeing here? Well, what we would expect, which is for very large transmission distances, you better use the Terahertz band. We're talking about extremely high path loss. But as you go to 1 meter, you actually have several mountains, or I would say several windows, and each one of these windows is actually several gigahertz wide. So what the terahertz group from IEEE standardization groups is doing is to focus on one of the first windows, actually, around here at 300 gigahertz. That's interesting. That if we reduce our transmission range just a few millimeters, centimeters, we see, okay, there are some absorption that will create some problems, but we should not limit ourselves just to the first window. Up to this point, however, I mentioned that, okay, there is this absorption which takes some energy from my wave, but that's not the only thing. Actually, what's happening is the following. As you can imagine, these molecules that they are vibrating, they are re-radiating part of the energy. This re-radiation of part of the energy is at the same frequency, but out of phase. This is why we can refer to this as molecular absorption noise. This noise is limited, which means that even if you irradiate the molecules with a huge power, they will not just vibrate more. They just vibrate or not vibrate. That's the main idea. So this noise, which is not the typical classical additive white Gaussian noise, has this shape. Again, in the x-axis, I have frequency from 0.1 to 10 terahertz. In the y-axis, distance, millimeter up to kilometer. And the color is the noise temperature in Kelvin. So again, what we're seeing here, well, if we go farther distances, we may have problems. But for short distances, this is not a problem. The main difference from this noise, however, is that this is correlated with the signal I'm transmitting. If I'm transmitting, I will create noise. I'm irradiating those molecules, and those molecules are vibrating. If I'm not transmitting, and I wait some time, after the relaxation time of the channel, those molecules will stop moving. At least, of course, as long as there is temperature in the system, molecules move and vibrate and everything, but they will not vibrate at terahertz frequencies. That's the clue.
Why, if you're saying that this noise is induced by the transmission, so why don't you call it signal, not noise? I mean, if somehow you create a transmitter and this output is the result of...
Okay, because we interpret it as noise, because it's actually kind of out of phase. So we cannot think of it as directly as part of the signal, even if we create it. But that's correct. Actually, that's one of the things that we then exploit when we create some communication scheme for this. Indeed.
But why is it depends on the distance. If this comes out of phase, whether it's 1 millimeter or 1 meter or 1 kilometer,
actually
they
here
are all out of phase, right?
Okay, what we see here is that it depends on the distance, mainly because we're assuming a uniform concentration of molecules. So the farther you go, the more molecules you have vibrating. So at the end, the more noise you end up gathering, but up to a point, the bound is 290 K.
Oh, you mean the whole meter? You mean this 1 kilometer is a molecular meter?
Yeah.
Okay.
Yeah. So longer distances actually mean more molecules vibrating. Because we are assuming a uniform distribution. We can change that. We can decide, no, there are molecules in this path, but maybe there are not so many.
Not in the air.
Exactly.
Yeah. Okay.
So how long does it take for a channel to settle down, so to speak?
Actually, a little bit, not that much. What do I mean by that? I will explain in the next slide why it is important, but we are talking about few, what would I say, picoseconds, something that. The problem is that this is very nice, but I guess that we will end up coming very soon. Somebody you will ask. This is true, but what happens when you have a network and everybody's transmitting and everybody's communicating? At the end, you will see that this noise is usually there. But let's reach that point in a few slides. Okay, I mentioned before, people working on macro scale, they say, no, you should focus on a single window. And we say, well, we don't see that need. Okay, let's do some capacity analysis, channel capacity analysis for different power allocation schemes, and let's see what happens. Here, okay, this is the classical expression for a frequency selective channel. And what we have already is we have our node. And the idea is that if we chop the channel, we divide it into very small bins, we can assume that within every bin, the noise is kind of flat, right? We already have the noise expression, the attenuation expression. We can play with this S, the way in which we allocate the power. Should we focus on one window? Should we spread it out? So actually, what we did is just to set a bound. First, we look at the optimal way of allocate this power over these windows we have. It would be water filling. Then we say, for simplicity, we just allocate the power in a flat way, I mean, distribute it in frequency. Alternatively, we can say, okay, no, let's look at one of their transmission windows, 350 gigahertz, 70 gigahertz bandwidth, and let's see what happens. And more interestingly, let's try to use some, well, what would correspond to the power spectral density of very short Gaussian pulses. Why Gaussian pulses all of a sudden? Well, if you take a very short pulse, you make, for example, 100 femtoseconds. This is what we are showing here. This is the first derivative of a femtosecond-long pulse, 100 femtosecond-long pulse. We know that its power spectral density will have the main components in the frequency of the Terahertz band. That's interesting, but why do we care about this and not many other options? Well, we know from people working, for example, on ultra-wideband or optical communications that pulse communications sometimes are good. No, we can learn something. But for sure, what they allow is to develop simple and energy-efficient transceivers. Moreover, these femtosecond-long pulses, it's not that we just decide to use them. Actually, they are already being used for nanoscale imaging and sensing applications. So it was like, well, maybe we can try to reuse some of the technology and the knowledge that they have for the transmission of pulses. And before you say, but okay, this is nothing new, this is comparable to ultra-wideband. Well, of course, everybody that transmits pulses, ultra-wideband was not the first one to transmit pulses. So what do we see? Well, this would be the channel capacity for the different power allocation schemes. In the x-axis, I have the transmission distance from few hundred of micrometers up to 1 meter. And in the y-axis, I have the capacity in bits per second. The top line is the green line, is the upper bound, is the optimal power allocation scheme, which we achieve with a kind of water filling. Of course, it's the optimal. We're talking about, for very short distances, transmission of up to, hundreds of terabits per second. That's fine. Overlap in the short range with this green line, we have another line, which is, well, actually, the orange one is the optimal, the green one is the flat allocation. Allocating over 10 terahertz, a flat signal means actually generating kind of delta in time. That's almost impossible. So it's interesting, but okay, what we're seeing is that for the short range, it's interesting to try to distribute the power. This blue line here, actually 2 orders of magnitude below what these other two options are, is actually what happens when we just look at one window. Let's say, no, we have our power, we just put it totally in the first window at 350 gigahertz. That's fine, but we are 2 orders of magnitude below what we could do. But wait, when we go to higher transmission distances, that's not the case. And what is this red line? This red line is the transmission of pulses, very wide frequency speaking pulses, very short in time. So what we are seeing, okay, look, for short transmission distances, okay, we are not the optimal, but we are close, we are comparable to the optimal. And of course, as we go to higher transmission distances, this is no longer the option. Above 1 meter, definitely you don't want to spread your power. So actually, as one of the conclusions of here is say, look, if these people are doing already these pulses for nanoscale imaging and sensing, maybe we can learn some of them. We can also take some of the solutions, hopefully not the problems, from impulse radio ultra-wideband. and try to use them. Well, that's an option. What did we learn out from this work? Mainly that, of course, the terahertz channel depends on the composition of the channel and also the distance, or said in other words, how these molecules are distributed along the path. The main factor coming, even if we can account for all types of molecules, but for the transmission distances we're talking and the frequencies we're talking, the main problem comes from water-vapor molecules. That's fine. And well, we can see that, well, even with relatively simple communication schemes, such as the transmission of pulses, we may be able to achieve terabits per second. But again, all this analysis does not take into account that we are targeting some very simple things, some very simple architectures. So, okay, what was next? We said, okay, we have these nano antennas for terahertz. We have this channel model for terahertz communications. We have seen that using pulses can be interesting. There are some problems, that's true. But, okay, why don't we try to build up some very simple communication scheme based on these pulses, and we use it for our communications? Okay, so actually, the scope of this paper that I'm going to present now was not to propose to use pulses. The scope was to try to do some capacity analysis for a nano network or a network of nano-things when we are using, well, terahertz band communications. In this case, pulse-based communication. The idea of this scheme is very simple. Again, we cannot expect fancy multi-carrier modulations, but we can expect some simple things. For example, imagine that a nano-thing needs to transmit a stream of bits, zeros and ones. A 1 is just transmitted with a single pulse, like let's say a pulse which is 100 femtoseconds. The energy of this pulse can be very low. Actually, our results were shown for 1 picojoule of energy per pulse, which is kind of this. Then, if we need to transmit a 0, actually we remain silent. By remaining silent, we don't consume energy. And, well, you will say, but how can you distinguish the fact that you are silent from the fact that you are not transmitting? Well, the idea here is that if we can somehow create some preambles that nano-things can exchange after the preamble, you know that nothing means 0. That's it. It's not that, of course, you can create some errors. Okay, then if you have errors, you will need some error recovery mechanism. And the idea is that we separate these pulses in time. So we wait enough time in such a way that the channel has recovered kind of original state. Again, we're using pulses mainly because we have seen that people are using them in nanoscale imaging techniques, and because those will provide us with a simple transceiver design, even if there may be other problems, like I could mention later. So for the single user case, imagine that there are just two users communicating. We have a binary input, zeros and ones, and we have an asymmetric binary channel. Asymmetric, why? Because when I transmit ones, there must be some noise. I'm creating that noise. But when I transmit zeros, actually, it's not that there is no noise, but the noise level is much lower. So we have an asymmetric binary channel. Because of that, actually, the capacity of the channel is not achieved for the uniform source distribution. It makes sense. If when you transmit zeros, you have less chances to make an error, you prefer to transmit more zeros than ones. Of course, if you're silent all the time, you don't transmit information. So there is this compromise, and this is what we obtain when we compute the capacity for the maximum of the source entropies. No, for the maximum of the source distribution. So what we see here, actually, in this figure, in the x-axis I have distance, again, from few hundreds of micrometers up to 1 meter, and in the y-axis I have capacity in bits per symbol. What I see here is that, okay, for the typical additive white Gaussian channel, which is a symmetric channel, after some distance, well, the capacity will go to 0. Why? I mean, mainly because what is happening here is that after some distance, you don't have any signal, you just have noise, and you don't know if the noise comes from a 0 or from a 1. That's it. That's a typical channel, binary channel. But when we look at the terahertz channel, we see actually that even if we increase our distance for a while, there will be something which is very interesting. If you are a device, you are expecting the reception of a pulse or a 0, and you receive something which, even if it's very low, it looks like noise. Actually, it is noise. And you know that that noise has been it can only be generated by somebody who transmitted. So actually, let's say the following. This line maybe it's not realistic because it's assuming that there is no noise absolutely when you don't transmit. But as long as your noise is lower when you don't transmit than when you transmit, you can actually, your receiver can end up guessing that somebody was transmitting just because there is noise in the channel. So that was one of the things that we...
But this noise is in the channel?
Yeah.
Just receiver noise?
That's noise in the channel. In addition, we may have to add the receiver noise. The problem is that we try to include some noise at the receiver. And then we have another problem. Why? There is no noise for graphene-based components. And there are like two big groups. A group is saying that there are many problems in thermal noise in graphene. Some other groups are saying that there is no thermal noise in graphene. So we have these two extremes. So right now we just look at the channel. Of course, these results will change when we take into account a noise model for graphene or whatever our transceiver architecture is, indeed.
So why does the capacity never increase? Like it increases and then...
Okay. Imagine the typical binary detection problem. You have two Gaussians. These Gaussians, they cross at one point. When you are at very short distances, it's very clear to distinguish the point at their cross, but as you go farther, the amplitude of your pulse go low. So actually, one of the Gaussians is moving towards zero. The other was already in zero because it's being silent. Plus, what's happening is that there is a point in which the two Gaussians became similar. Why? Because the amplitude of the signal and the noise that it has generated are comparable. So actually you can compare your signal, what would be the Gaussian of the transmission of nothing, of silence. But after that, because of the noise, you still have some noise. You have more noise than actually that correlated signal, that amplitude. So what's happening is you have still a thin Gaussian to detect at zero, and around it, you have this noise level. So you can go a little bit up because you know that as long as you receive something, it will be its noise. Only if you don't receive anything, it means that you receive zero. That's this strange behavior. Of course, this is not fully true. I would like to cut it, for example, here. Why? Because your signal will not propagate for always, will not keep creating noise. There is a point in which this is cut. But again, we did all the analysis thinking of short distance with a specific number of molecules. So to include now the effects that at some point there is nothing left to create these vibrations is not in here. So this is why I don't show anymore above 1 meter. Don't want to. This is valid for short transmission distance. But again, this is okay for just one user, one device, but in a real network, I have many devices transmitting, and that's okay. We will have interference. We expect that. However, this interference may not be that bad. Why? First of all, we are talking about the transmission of very short pulses. So you can understand from the classical way that having collisions between pulses which are 100 femtosecond-long is actually unlikely. In addition, well, if you transmit pulses, you may have collisions. But when you are silent, actually, when you transmit a zero, it's perfectly fine if you collide with somebody else who transmitted a zero. So we should distinguish between collisions between ones, between zeros, and between zeros and ones. So again, if you try to take into account this fact and try to compute the capacity for this new case, what you will see is that two things. Again, what is happening here is that when you transmit ones, you potentially are creating interference, you are creating noise, and well, only people who are also transmitting ones will interfere with you. That's one case. When you are transmitting zeros, you are not creating interference to anybody, you are not creating noise, but whoever is transmitting a pulse will interfere with you. So there is this compromise, and again, ideally, of course, if everybody is transmitting more zeros than ones, if the network tends to be silent, of course there is no interference, but you cannot transmit information if you are all the time transmitting the same bit. That's one problem. But again, when we compute the capacity, we compute the capacity for the maximum of the source distribution that gives us this. And actually, these lines here, what are shown, are not shown for the typical equiprobable distribution between 0.5 for 1, 0.5 for zeros, but it will be for source coding in which there are more zeros than ones transmitted. So what are we seeing here? I mean, the idea here is that number of users increasing in this direction, increasing distance. What can we see? Well, that even when we go up to very large number of users, let's say 10,000, because we are spreading these pulses like much more than what our signal is, we can still support many users transmitting at high bits per symbol, at high bit rates. That's interesting for the network capacity, but what is happening to the single user? Well, one single user, what we're actually seeing is that at whenever you go above, like say, hundreds of users, it's then when your performance really starts to decline. But we are talking that you can have actually like many nodes, let's say 1 node per square millimeter, transmitting up to almost terabits per second. That interference will not be such a problem, noise will not be such a problem, but again, everything depends. What we did starting from this work is that, as I told you, you would like to transmit more zeros than ones, because what you obtain by that is that you reduce the noise and interference. But you need to transmit at the end binary streams, if not you're not transmitting information. So I'm not explaining it here today, but what we did from that is to investigate a little bit some other possible source coding techniques and channel coding techniques. And we did some analysis, which was published in ICC 2011, in which we were showing that actually there is an optimal coding weight, which means the number of ones versus zeros that you have in your coding words, that allows you to maximize the information rate while minimizing still the interference of the noise, which is a kind of practical analysis of this. Actually, yes, I have the slides here, but that was the idea. In any case, okay, as you can see up to this point, the devices will be coming. It may take us some time, but we will have them. The terahertz channels has some problems, but also some opportunities for us. We have seen that, for example, the transmission of pulses is a very simple scheme that may work. So, well, maybe that's interesting. Of course, transmission of pulses also introduces synchronization challenges, and this is something that we are also working on. But as we move towards network problems, we may have many problems. Some of them are already in the Internet of Things. Here, they will just be like much worse. Why? Okay, for example, the Internet of Things starts by saying that everybody should have an address, a unique address. How are we going to give address when we have trillions of these things? That's a problem. Maybe we don't need to have unique address for everything. We just need unique local addresses. Who is going to assign these addresses, or how I can learn the addresses from the other? What is an address here? I mean, we're talking about very simple devices. I cannot pretend them to be able to handle very complex addresses. Or how is mobility? What is mobility here? These nano things, there is win and distinct go. I mean, you know, there is a different mobility pattern here that should also be taken into account. Of course, we have not mentioned this before, but okay, I mean, in addition to addressing, routing, well, these things, the idea is if you are going to have a lot of them and you have to make them small, well, the idea is that maybe they are not that reliable. In addition, the channel can create disconnections if there is a sudden change in the concentration. All these problems may bring several reliability issues. So, okay, these are other things that we have to learn here. Moreover, again, this is coming from the Internet of Things. You can understand that if you cannot even see these nano things because they are around you or they are embedded in you, well, you have a problem, which is, okay, you don't know that they are there, so this is a problem. Moreover, they may be transmitting very confidential data from yourself. You need to protect that information. Of course, usually this information, if we are thinking, for example, of medical applications, this information may come as soon as possible to a gateway, like my watch or my cell phone. And from there, it's when I start to need also protecting that information. So, well, the idea that I want to transmit here is that, okay, we are working. Since I started my PhD, there are a couple, 2 or 3 more groups working on this, but there are not so many people working on this, and especially at this time, which, again, is the right time probably, it would be good to have more people trying to discuss this, to work about this, to have these kind of meetings that we somehow miss. Of course, the other thing is that we are actually always willing to work with people who has the device facilities. As I mentioned before, we are partnering now with 2 more universities to actually try to build something. Many people after this, they say, okay, that's nice, but I don't believe anything if I don't see it. I mean, I got rejections in which the first sentence is, I don't care about this paper. This research can be totally wrong because there is no device that supports it. Okay. I mean, as a student, when you get this paper, you get quite disappointed, but what do you think? I mean, you trust your advisor, say, okay, this is going to work. Then you talk to the device people, they say, it will take a long, but it will work. So that's what we do. Okay, so this is all from my side for now. I hope that you enjoyed the presentation, at least you learned something. I really had fun presenting it here today, so thank you.
Thanks.